The next presentation is going to be given by Pavol, Bielik, and he's going to talk about learning a static analyzer from data. It's being wired up. All right.
Yep. All right, so thanks. My name is Pavol. I'm a PhD student at ETH Zurich, and today I would like to present you a joint work with Besselin and Martin about learning a static analyzer from data. So why would we want to do such a thing? So as you all know, writing static analyzer is hard. It can be frustrating, it can be time-consuming, it can be brittle. And there are many people who already tried to do this, both in industry and academia. And if you look, for example, in one of the state-of-the-art systems, such as Facebook Flow for JavaScript, there is more than 400 contributors writing this software. But even though there is 400 people trying to improve the software, if you actually run it on real-world examples, it can still be unsound. So in this case, we have a simple JavaScript program that initializes an array and tries to access a threshold field of an array, which of course doesn't exist. And the tool correctly reports that there is an error on line 11, but here the error is missed. And the reason is that here we sort of access the data field indirectly by being it bound to the this variable, right? So the question we try to answer is, can we help writing static analyzer either fully or just partially by trying to learn it from data? And by trying to learn it, I mean trying to learn the abstract transformers. So the overall idea is that let's suppose we have a training data set. I'll explain in a while how we actually can get such a data set. Then assume we have a language that can describe the abstract transformers. And then what we would like to do is design a synthesis procedure which can synthesize an analysis in this language with over-approximated at the right places such that it can satisfy the training data set. And this has several challenges. So the first one is how can we update the data set in the first place? We don't want to have people sort of trying to annotate JavaScript programs and what the result should be. If we try to design the language to specify the transformers, first, we need to have it very general. We don't want to just have a combination of existing transformers, but we want to have a way to come up with the new interesting transformers that the developer didn't think about when designing the language. And finally, we have to come up with a scalable synthesis algorithm that can take these pieces and prevent overfitting such that the analysis is actually correct. So when I said that we want to learn a static analyzer, this is not quite true because we don't want to learn just any static analyzer, but we want to learn a static analyzer that we can interpret, so it's just not some black box with learn millions ways that does the classification for us, but we can look at it and integrate it with existing analyzers, but also something that is sound. And to be sound, we have to be clever about formulating the problem. So we have a first term, which is the standard in sort of machine learning, which says, let's try to find analysis that minimizes some cost over the data set. But then we have a requirement which says, we want to find this analysis subject to the fact that for all the training examples in our data set, the analysis is actually correct, right? So we will define soundness with respect to our training data set. We will not try to formally verify the analyzer. So once we do this, we can synthesize quite complex programs, such as this one. So this would be the analysis for the example I showed earlier that the Facebook Flow didn't handle. And as we can see, it has come up with some interesting predicates, such as the color has one argument, or the second argument is identifier, that were not put in front by us as a designer. And secondly, it has come up with a lot of corner cases that the analyzer or the developer would have to consider himself when designing such analysis. So let me now show you how we can do this by explaining individual steps one by one on an example of points to analysis. So the first one is that we would like to obtain the training data on which we can train. And as it happens, we already have a lot of programs that are available to us. And one thing we can do is we can simply run them. And this is kind of the beauty of the approach, that by simply running them, we can obtain a large amount of training data. So what we'll do is we first transform the program into abstract syntax tree representation, and then we simply execute it on a set of inputs, where for each read and write in a program, we will record what is the concrete object that was read and written to. With such a data set, we can then take each location in the abstract syntax tree and say that this is our training example. So for this given abstract syntax tree, for this location, if you run the analysis, it should output this object or an abstract representation of this object, right? Once we have the data set, we will try to define a language that can describe the abstract transformers. The way we do this is that we first describe a very generic template which contains a straight line programs that we describe as an actions and a predicate that can introduce branches in the programs. And the idea is that the action sort of define the result of the analysis. So for a points to query, the actions will describe that this value here points to the object that is located at this position in the program. And the predicates can restrict when this is actually true, right? And the nice thing about this formulation is that this is very general. We can then instantiate these actions and guards for this particular analysis. And also, we can then represent such graphs as decision trees, which is very useful because first, we can interpret paths in these trees as abstract transformers. And we can also use the techniques from the decision tree learning when we try to actually learn and do the synthesis. So once we have these two components, we try to do the synthesis, but it turns out that the synthesis alone is not enough. So what we try to do is introduce an additional component, which is the oracle, which once the synthesizer comes up with the candidate analysis, it tries to test it and find a counterexample for the analysis for which it doesn't work. And this is the standard Segis loop when we then take the analysis that was not in our training example training data set at the beginning, and then we iterate again. So how does the synthesis work? So the first thing we need to do is we need to define the cost function that we want to optimize. So this was our original problem formulation. And the cost function is quite simple, and it simply states we want to count the number of mistakes the analysis makes. So we will count 1 if the result is not equal to what we expect, 0 otherwise, and then we'll just try to minimize the number of errors the analysis makes. Unfortunately, if you just do this naively with this template language, it's quite untractable because there are millions of possible programs we can write in the leaves here. Then there are millions of other programs that we can define to split the predicates. So in general, this is too much. So the key idea here is that we try to do the synthesis in parts. So first, we'll synthesize a program that explains some of the data. Typically, this is really just a subset. Then we'll fix this program and try to synthesize a predicate that separates this data from the rest of the data set. And then we'll again fix the predicate here and refine the actual analysis further on. So to give you a more visual illustration, at the beginning we start with sort of trying to just synthesize some small analysis just as a straight line program that covers some of the data. If you're lucky, the cost is 0, which means that there are no errors, and we are done. The other case is that if the analysis covers some part of the data, in which case we will try to refine it further. To refine it, we'll try to sort of split the data set such that it separates the analysis from the data it can explain with the data it cannot explain. Again, if you are lucky, we can find a perfect split, but this might not be the case, so we might find one that is maybe not optimal. But what we'll do later on is that we refine further. And by refining further, we can find optimal split later on. The corner case here is that maybe there is no split, and in which case we just approximate the data set we are working with at the moment. Once we do this, the result is a candidate program analysis that we would like to now test whether we can find some counterexamples. And the way we do the testing is the naive approach would be, well, let's take a random training example. Let's try to mutate it. Then we obtain the correct labels by running this example, and we try to see if there is some inconsistency. The problem with this approach is that, well, if we do it really purely randomly, there is exponential number of choices. We always have to execute a program to obtain the correct label, which can be quite slow if we do refinement loop, and we don't really know when to terminate. So to address this, the key idea is we will try to take advantage of the analysis that we synthesized so far when we try to make these decisions. So instead of looking at the space of all possible programs as a black box and trying to sort of blindly pick points that might be interesting, we will take the analysis that we synthesized so far, and we will compute the path coverage, and we will sort of segment the training data set such that it covers individual parts of the analysis. In which case, even if the analysis has a corner case that covers very few examples, we can still efficiently sample from these few examples. In the next step, once we select an example to sort of mutate, the next question is where in the program we actually want to introduce the mutation. And here again, we can try to take advantage of the analysis and try to look what are the places that the analysis actually uses in order to compute the result. And we know that we have to modify some of them, right? If you modify places that the analysis doesn't even look at, this should not affect the analysis. And finally, once we pick a place where we want to do the modification, we have to decide what kind of modification we would like to do. And here we sort of introduce two concepts. So the first one is modification via equivalence modulo abstraction. So here the key idea is that we start from a program and we make modifications that are semantic preserving. And the semantic preserving is always defined with respect to the analysis we are trying to synthesize. So the idea here is that if you do any of these modifications, such that adding a dead code or renaming a variable, it should not affect the results of the analysis. And since it doesn't affect the results of the analysis, we can reuse the labels we computed before, and we don't have to have an expensive procedure that executes the program and obtains the labels for us. In addition to this, we also have modification via global jumps, which sort of try to jump from this equivalence class to another one and then perform local search again. And if we do this optimization, we can show that we can have more than order of magnitude improve in effectiveness of finding the counterexamples. So putting this together, we try to evaluate the approach for JavaScript, which contains lots of tricky cases. We took a conformance suit for the latest specification, which contains more than 15,000 JavaScript programs and associated test cases. And we tried to synthesize two analyses. So the first one was the points to analysis for this keyword in the JavaScript, and the second one is allocation side analysis. So to instantiate, really to give you an overview how to instantiate the general approach, we need to define these four things. So the first one is how we get the data set. In this case, the data set is just concrete object IDs that are collected during the instrumentation. The language is quite simple. So we have an actions that can move over the AST and traverse to the parts that are interesting for the analysis. And we have write operation that can condition on some parts of the AST when we try to write the predicates in the program, right? Such as the value of a node or type of a node. Then we have to instantiate the analysis by providing the abstract lattice and the abstraction and concretization functions. And then to test the analysis, we instantiate the oracle with types of mutations we would like this analysis to be semantic preserving, and then just some random mutations. The results are shown here. So these are sort of all the functions that we synthesized. As you can see, many of them are missed by the state-of-the-art analyzers, and many of them contain programs that have 30 to 40 or maybe even up to 100 instructions in the language, and cover up to from 6 to 18 different corner cases that one would have to specify manually. In this case, the learning time was about 14 minutes, which is quite scalable. The next experiment we tried to do is for the allocation side analysis. Here the dataset was much, much larger, so it was more than 100,000 training examples. We still found more than 900 counterexamples with around 99 refinement loops, and the whole synthesis took about 10 hours, where 3 hours were spent for synthesizing the programs and 7 hours for trying to find the counterexample. And this is sort of the skeleton of the learned analysis. It's quite large. It contains about 200 branches. So to summarize, I presented an approach to learn static analysis from data. The nice thing is that this can be mostly automated, where we can exploit the fact that we can run the programs to obtain the concrete traces which are under approximation of all the possible behaviors, and then we try to synthesize analysis which is sort of abstract enough that the designer doesn't have to actually know what the analysis is supposed to do when designing this. Yeah, so thank you.
Let's give him a round of applause, please. So we do have 2 minutes for questions. Come on, guys. You know you want to ask it. Yes, please. You could come forward to the microphone.
Does it work? Okay. So sorry, maybe I'm missing something there. Were there any loops in your language then in the analysis that you're generating?
No.
So how do you compute fixed points? You're producing static analysis automatically, right? And all the static analysis I know use some sort of fixed point.
Yeah, so the fixed point in this case is a bit indirect, because what the analysis computes is for a program, it produces where the answer is located. And then when you go to that place, you can run again the analysis and maybe go to another place and then iterate until you actually find the result. So in terms of points to analysis, it will tell you this variable is pointing to the same variable as this place is pointing to. And then you go there and run the analysis again and run the analysis again, right?
All right. So you're producing the transformers, and the application of the
transformers. Yes, application of the
external.
transformers is done until fixed point.
That was all my question.
So you mentioned that the abstract domain has to be given as an input to your method.
Yeah.
And I know that there are different methods of then synthesizing the abstract transformers.
Yeah.
And my question would be, how does your method compare to them in terms of precision? Because there are actually methods that use SMT solvers to synthesize the proven to be optimal abstract transformers.
Yeah, so yeah, this is true, but this is typically done, at least as far as I know, for numerical domains.
Okay.
And here the abstract domain is actually very simple. For example, for points to analysis is mostly flat, so this is not that hard to obtain. So we are not aware of any work that would do these kind of analysis that we try to do.
And you haven't tried it on other analyses, such as like relational analyses between local variables?
No, unfortunately no, so I cannot answer.
Okay.
All right, let's thank the speaker again.